You know, we walk around on a planet that feels, well, solid. But the truth is, it's anything but. It's in constant, powerful motion. And that's what we're talking about today, the incredible story of plate tectonics. Let's kick things off with a number, just a single staggering number, 28,000. So what is that? Well, between 2011 and 2012, that's how many earthquakes rattled the Greek island of Santorini. I mean, think about that. In just a short period of time, it was a seismic swarm of just incredible intensity.
So, you gotta ask, right? What in the world could shake a single island 28,000 times? This wasn't just some random collection of tremors. No, this was a clue, a symptom of something much, much bigger happening deep beneath the surface. And here we have it, the culprit. Scientists figured out that something like 300 million cubic meters of molten rock, magma, was forcing its way upward, cracking and shattering the rock as it climbed. This one event, on a small island, it's the perfect window into the massive forces that are constantly, and I mean constantly, reshaping our entire world. So that really brings us to the big picture here, these giant interlocking puzzle pieces that make up the very ground we stand on.
The theory that explains all of this, it's plate tectonics. And the core idea is pretty simple, actually. The Earth's surface isn't one solid shell. Nope, it's broken up into more than a dozen massive, rigid plates, and they're all moving.
You want a great way to picture this? Think of a cracked eggshell. Seriously, each of those broken pieces of shell is like a tectonic plate, and they're all just kind of floating on top of the hot, gooey, slowly flowing rock of the mantle underneath. It's this incredibly dynamic, restless system. But, you know, this idea didn't just pop up and get accepted overnight. Far from it. Back in 1912, a guy named Alfred Wegener came up with this idea of continental drift. But pretty much everyone thought he was crazy. And the big problem, the fatal flaw in his theory, was that he couldn't answer one simple question. What force could possibly be strong enough to move entire continents? It actually took another 50 years and a ton of new data from exploring the ocean floor to finally crack that puzzle.
All right, so let's get into that puzzle. What is the engine that drives this whole planetary machine?
I mean, this was the central mystery. What's the driving force? Wegener had this idea that continents just sort of plowed through the ocean floor. But physicists were quick to point out, correctly, that that's impossible. The real answer, it turns out, was way, way deeper.
And this is it. This is the engine, mantle convection. The best way to think about it is like a giant pot of really, really thick soup on a stove. The hotter stuff at the bottom rises up, it cools off near the top, and then it sinks back down. It's this super slow but incredibly powerful churning cycle. And that is what moves the plates.
Okay, so how does that soup actually move things? Well, it creates two main forces. First, you have what's called ridge push. Think of it this way. Where that hot material rises up at mid-ocean ridges, it creates a little hill, and gravity basically pushes the plates apart. But the real heavyweight champion here is slab pull. As the cold, dense edge of a plate sinks back down into the mantle, its own immense weight literally pulls the rest of the plate along for the ride. It's a pull, not just a push.
So if all these massive plates are constantly on the move, what happens when they run into each other? Right. Let's head to the action zones, the plate boundaries. Basically, there are four main ways these plates meet up. They can pull apart from each other, which lets magma well up and create brand new crust. One can dive, or subduct, right under another one, melting back into the mantle. Two continents can crash into each other head-on, buckling up to create massive mountain ranges like the Himalayas. Or finally, they can just slide and scrape past each other horizontally.
And here's the thing. This is where it all clicks into place. These boundaries are not random. They form these really specific belts around the globe. And guess what? Those belts perfectly line up with where we find almost all the world's earthquakes, volcanoes, and major mountain ranges. It suddenly all makes sense. It's the unifying theory of geology.
Okay, so this process seems so fundamental, right, to how a rocky planet should work. Which makes you wonder, why does it seem like it's only happening here, on Earth?
I mean, when we look out at our planetary neighbors like Mars or Venus, we see volcanoes, we see signs of quakes, but we don't see this system of moving plates. Their surfaces are like one solid lid. So, what makes Earth so special? Let's break it down. Take Mars. It's just too small. It's cooled off so much that its crust is just too cold and stiff to break apart. Then you've got Venus. It's about the same size as Earth. It's got plenty of heat inside,
but it's missing a second, absolutely critical ingredient.
And here they are, the two secret ingredients for Earth's special geology. Number 1, enough internal heat to keep that mantle turning away. And number 2, liquid water, lots of it. Water acts like a lubricant, basically making it easier for these massive plates to slide around. You need both. Without them, the whole system grinds to a halt.
Okay, let's bring this huge planetary story all the way back home, back down to a human scale. Because whether we realize it or not, we're living right on the front lines of all this.
Yeah, this constant movement isn't just some abstract idea in a textbook. It's happening right now, and it's a very real danger. And the most famous example, of course, is the San Andreas Fault in California. It's a huge boundary where the Pacific Plate is scraping its way north, right alongside the North American Plate.
And get this, researchers say the southern part of that fault is capable of unleashing a magnitude 8.1 earthquake. That's a truly staggering amount of energy just waiting.
The cost, well, it would be catastrophic, both in human lives and economically. A big study back in 2008 estimated that a major quake on the southern San Andreas could cause something like 213 times $1 billion in damage. That's the reality, you know? That's what it means to live on this restless planet.
And this all circles back to a really core idea in geology, summed up perfectly over 200 years ago by a guy named James Hutton. He said, the present is the key to the past. And what he meant was that the same slow, powerful forces we see today, the ones moving continents, building mountains, causing earthquakes, those are the exact same forces that have been shaping our world for billions of years. So that leaves us with one last big idea to chew on. The very same forces that create the world's most stunning landscapes, our mountains, our oceans, are also the source of some of its greatest threats. It's a double-edged sword. And the challenge for us, really, is figuring out how we understand and how we adapt to living with that kind of incredible power right under our feet.